an atom. And in the atom, we have these electrons living, occupying different energy states. So these different energy states that we are very familiar with using, and we've seen them already this year, are what we call ground states. So when we're talking about atoms in a normal situation, we are talking about atoms with electrons in their ground state. If we can provide these atoms with energy, the electrons will, what we call, get excited, but they can move to higher energy levels. Eventually that energy is going to disappear or be used, and so once the energy source disappears, the electrons will move back to their ground state, which is more stable for them. But as energy can't be created or destroyed, that energy needs to be transformed into something. As the electrons drop back, they emit energy in the form of light. And that light will be a different colour depending on the energy level that the electron has been risen to, and that will be specific to each different atom. So each atom has a unique, what we call, fingerprint, and the colours that are released by an atom are called their emission spectra. And you may have seen this before in the flame tests. If you haven't, here's a quick example of that.
In the 1850s, Robert Bunsen and his research collaborator Gustav Kirchhoff conducted a series of experiments to determine why substances emitted specific colors when placed in a flame. The color they determined indicates what elements are present in the substance. For example, if sodium is placed in a flame, they observe shades of yellow. Copper, shades of green. Strontium, shades of red. That was a good one. While watching the experiments, Kirchhoff was reminded of how a prism spreads light into a rainbow of colors. So, using a prism and the pieces of a small telescope, Bunsen and Kirchhoff built the first spectroscope, an analytical device they hoped would help them see the spectra coming from heated substances. And it worked. As an element was put into the flame of a Bunsen burner, the light from the heated substance passed through the prism of the spectroscope, where it then spread into a ribbon-like spectrum of colors, riddled with dark lines. The combinations of bright colors and dark lines were like barcodes indicating what atoms were present. When burned, each element produced a completely unique spectrum. Using their spectroscope, Bunsen and Kirchhoff were able to discover two new elements, cesium and rubidium. One day, Bunsen and Kirchhoff decided to test their invention with sunlight. It produced a spectrum that featured two lines that were identical to those in the spectrum produced by sodium. Bunsen and Kirchhoff had discovered the presence of sodium in the sun, 93 million miles away. Suddenly, scientists had a tool to help them study the chemistry of the heavens.
Liftoff. We have liftoff.
Today, the legacy of this great discovery lives on in the exploration of space. A form of spectroscopy is being used to study the atmospheres of planets, to search for signs of water, signs of life.
So you can see the different colours according to the different atom type, and that's got to do with those energy levels that the electron can be excited to and therefore fall back from. If we consider this from an analytical perspective, we can use some fairly technical machinery called atomic absorption spectroscopy. And what we can do is target the wavelength specific to the atoms that we suspect we have. So, for example, we may be concerned with the concentration of lead in water. And that would be a specific concern in places like Port Pirie, where there's a lead smelter. And so if we are going to test water for lead levels, we can use this atomic absorption spectroscopy equipment, and we can put in a wavelength that is specific for lead. So that means that only the lead atoms are going to absorb this wavelength, and excitation of those electrons is going to occur. What we can do is we can then measure how much absorbance has occurred by those lead atoms in that mixture. So the higher the concentration of lead atoms in a sample, the more absorbance we are going to have. So to do this, we would create a series of standard solutions. Those standard solutions would have a known concentration, and we would have increasing concentration of those standard solutions. We would then be able to measure the absorbance and create a calibration curve. And from that calibration curve, we could then measure a sample that we have collected, so an unknown amount or concentration of lead. And we would then be able to measure the concentration of lead based on that calibration curve. If our sample was too concentrated and didn't fit on that calibration curve, we would need to dilute it so that it did, because we are only confident that we have the absorbance and concentration for our calibration curve data, because we're not sure about the trend that will happen afterwards. We would need to measure and have a separate curve for higher concentrations. So an easier way to do that is to absorption spectrometer has some important components. It has a halocathode lamp. That halocathode lamp is it sends out a specific wavelength to the metal we are investigating. So what we do is we have a different lamp according to what we are investigating at the time. So if we're investigating sodium, we'd have a sodium lamp. If we're investigating lead, we'd have a lead lamp. If we're investigating cadmium, we'd have a cadmium lamp. So it will send in the signal of the wavelength we are interested in. That signal gets sent into a flame. The flame is there to excite the atoms so that we can what we call atomize them. So we want to be dealing with individual atoms instead of a clump of material. So we use a flame so that we separate the atoms. And we also have so because our samples are in liquid, we need to get them into mist. We have something called an atomizer, which basically separates the liquid into a spray, and it sprays it into the flame. The signal is then absorbed, so the wavelength will then be absorbed depending on the concentration of atoms, and that signal will be sent through to a detector. It's important to note that this process. Here's a clip which goes into detail about the process of sampling, and it's talking about sampling for lead content in fish, and it will go through the entire process of how they would go about using this AAS in a real world scenario. So it goes into it in quite a bit of detail, but you should be able to understand most of the detail, and it will help you to put this process into context as to how it's used.
What has this fish and world-famous CSIRO scientist Alan Walsh got in common? Well, the answer is both spent their working life in Australia. Walsh went on to receive a knighthood and great scientific notoriety for his work in developing this instrument, the atomic absorption spectrophotometer, which was conceived in a flash of inspiration in a Melbourne vegetable garden on a Sunday morning in March 1952. The fish went on to star in this video and also became the second course at a fish and chip shop in Ultimo on a Sunday night in March 2007. Have you ever wondered how the spectacular colours of a fireworks display are generated, or how neon signs have such vivid colours? Well, it's all to do with some simple atomic physics. When chemical elements are exposed to high temperatures or voltages, they give off coloured light. When this light is passed through a prism, it appears as a series of bright coloured lines called a band spectrum, which indicates that light is only being emitted at specific wavelengths or colours. Each chemical element has its own set of colours related to its electron energy levels, and this is as individual as a fingerprint. Alan Walsh was able to use these unique properties of elements to develop the atomic absorption spectrophotometer, often abbreviated to AAS, a tool that revolutionised quantitative chemical analysis, providing, in Walsh's own words, a quick, easy, accurate and highly sensitive method for determining the concentrations of over 65 chemical elements, in the process rendering obsolete a raft of slow and sometimes dangerous wet chemical methods. One example of this is the determination of gold in metals, where the wet chemical method took 1 month to complete. The analysis performed on the AAS takes 10 minutes. AAS analysis has found many important applications all around the world, in areas as diverse as medicine and biochemistry, food analysis, environmental analysis, metallurgy and mineral exploration, and has been described as one of the most significant advances in chemical analysis during the 20th century. The technique is mostly confined to metals, although there are a few exceptions such as silicon, arsenic and germanium. But it's not just the diversity of materials that can be analysed that makes AAS such an important analytical technique. The detection limits and precision of analysis are also outstanding. AAS can routinely perform analysis at the parts per million level, or milligrams per kilogram, and detect extremely minute concentrations of materials, such as the levels of lead in this fish. This can be done with accuracies in the 1 to 3% range. The AAS has 5 main components: the hollow cathode lamp, the burner, the monochromator, the detector and the readout. The hollow cathode lamp is the key to the success of this technique, and it's the only component that's not shared with other analytical techniques. Each element requires its own personal HCl, a device that generates wavelengths specific for that element. It means we have to have many hollow cathode lamps. It also means we can only analyse one element at a time with AAS. These days that's seen as somewhat of a limitation. Some research instruments replace the HCl with lasers. This makes them more sensitive and also allows them to analyse more than one element at a time. You can think of the flame as the sample holder in AAS. It contains the vaporised solution where the gaseous atoms we're trying to analyse absorb light from the hollow cathode lamp. Notice that it's very wide. This allows a lot of sample atoms to contact the beam to increase the total absorbance, making the instrument more sensitive. A small amount of sample is sprayed into the burner, which uses either air acetylene or nitrous oxide acetylene to generate a very hot flame of between 2100 and 2800 degrees. This releases the metal atoms from their chemical compounds and turns the sample into a vapour. The monochromator ensures that light of only the same wavelength as a hollow cathode lamp gets into the detector. We need this as other elements in the flame will also emit light at different wavelengths when in the burner. This can cause false high readings when they arrive at the detector. The detector records the amount of light emerging from the flame. If we increase the amount of atoms we're analysing in the flame, the amount of light arriving at the detector will decrease and the absorption value will increase. The more of the analyte we have, the greater the absorbance value. In order to perform an analysis with AAS, we need to complete a few simple steps. We'll use the analysis of lead in this fish as an example. The first step in the process is to get the fish into a form that can be analysed. AAS only analyses liquids. Solids and gases must first be turned into a liquid before we can perform any sort of analysis. Once we have our sample ready, we need to prepare a calibration graph. This is done by preparing a set of accurately made solutions, then recording their values on the atomic absorption spectrophotometer. You can participate by preparing your own calibration graph.
First need to zero the instrument with a blank, which is simply dilute acid. Okay, we're now ready to move on to the first standard, which is 5 milligrams per litre. Invert that to make sure it is completely mixed. And we have a reading of 0.125. To the next standard, the 10. A reading of 0.21 and 15 milligrams per litre. Reading this time of 0.32 and our highest concentration standard at 20 milligrams per litre. Giving us a reading of 0.42.
Next, we plot the absorbance values of the calibration standards on the y-axis and their corresponding concentrations on the x-axis. We can then use the calibration graph to work out the concentration of our unknown in our sample. In this instance, we take the absorbance value of the sample, come across to the graph, and then move to the x-axis, where we read off the concentration. See if you can work out the concentration of the solution that Brian's working on.
This is our dissolved up sample prepared fish, now in solution, giving a reading of 0.27. And after we've finished all the solutions, we need to clean out the internals of the instrument by flushing it with some more dilute acid.